Hi, my name is Christopher Meyer, and this is my Lab 5, Magnetic Braking with Faraday. So, introduction, the goal of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, and then use this data to model the magnet-tube interaction computationally. Once we have the computation model, our next goal is to compare computational predictions with the observed data. Our results from the lab, as well as the code from the experiment, we got 1.098 seconds that the magnet was falling through the tube, and the code said 1.156 seconds. The fundamental principles we look at in this lab are Faraday's law, which is used to find the current in each ring within the tube, which can be seen as EMF equals the change of flux over the change of time. The Biot-Savart law, which is used to find the magnetic field of each current-carrying ring. And then Newton's third law of motion, which is the force exerted from the magnet on the tube is equal to the force exerted by the tube on the magnet. So in the lab, the procedure was first to determine the north end of the magnet using the magnetometer app, then record the magnet dropping through the aluminum foil, find the timestamps of entry and exit to determine the total time in the tube, and repeat this 5 times, and then find the average of these 5 trials. So lab data, we got that the tube length was 0.356 meters, the foil width was 0.005 meters, the roll radius was 0.02 meters, mu was 3.11 amp meters squared, which we found from lab 3. The magnet mass was 0.0241 kilograms, and the average fall time was 1.098 seconds. As you can see to the right, these are 5 trials, with the first trial being 1.05 seconds, second 1.19, third 1.03, fourth 1.15, and fifth 1.07. Once we were done with the lab, we created a computational model to represent this lab. The first thing you can see is the top right is the loop that we run to calculate the change of magnetic flux over the change of time as the magnet is falling through the tube. The bottom left is used to find what the magnetic force is on the magnet, as well as to find the net force total, and then use this to edit a graph to see the bar's velocity and bar's position change over time. And then to the right, you can see the loop that we've used to find the induced current by the tube that was created from the falling magnet. Once we completed the lab code, you can see now here are our results and models. To the left, you can see a red and blue ring. The red ring represents a clockwise movement of the magnetic field from the magnet falling, and the blue is the counterclockwise movement of the induced current. And at the end, on the right model, you can see that there's only a red magnetic field because now the bar has exited the tube. And to the right, you can see the velocity versus time graph, where as the bar is initially entering the tube, the gravitational force is greater than the magnetic force, but once it reaches about the middle, the magnetic force equals the gravitational force, and then the velocity becomes constant because the net force becomes 0. And then it begins to drop off again once it leaves the tube. And you can see the computational model came out to be 1.156 seconds was the total time that the magnet was in the tube. Now, from the computational model, we were able to interpret that the model shows the force of gravity pulling the magnet down while the magnetic force due to the induced current acts upward, which causes the acceleration of the magnet to decrease. Now, when the magnet's in the middle of the tube, the magnetic force equals the force of gravity, so it experiences no acceleration, and it's seen by the constant velocity. The red ring shows a clockwise current, while the blue shows a counterclockwise. And finally, the change in magnetic flux increases downwards in the negative y, so the induced current acts counterclockwise to oppose this change in flux. And if the magnet was flipped, the magnetic flux would increase in the positive y, so the induced current would therefore move clockwise. Finally, reflection questions. The first one is, if the resistivity of the conductor were reduced as close as possible to 0, how would the dynamics of the falling magnet change? Now, with the resistivity approaching 0, the induced current would also therefore approach infinity. And since the current is approaching infinity, the force slowing the magnet velocity would increase, and the magnet's velocity would theoretically eventually approach 0 meters per second. Now, what if holes or slots were cut into the tube, and how would this affect the ring currents in your model? Now, with holes, the tube would have a lesser effect on the magnet due to a decreased induced current, and therefore the magnet would fall faster. Thank you, and that is my lab.